Hello and welcome to today's video. In this video we're going to talk about one other integration rule that is often useful, and that rule is called integration by substitution. Again, the idea is to transfer one of the rules of differentiation, and this time we're going to have a look at the chain rule. We call that chain rule, so what we can do is if we want to differentiate a function of the form f of g of x, and we can do this by differentiating f first, evaluating that at g of x, and then multiplying with g prime of x. Now let's say we have an antiderivative for f, maybe, yeah? So if capital F is an antiderivative of f, then the following is true. Applying this chain rule, we can have a look at the function capital F of g of x and differentiate that. If we do that, what we get is capital F prime of g of x times g prime of x. And as capital F is an antiderivative of f, capital F prime is the same as f. So we have f of g times g prime. And that means we can use that relation to formulate another rule of integration. So in particular, the function f after g is an antiderivative of small f after g times g prime. And that's basically the content of this so-called integration by substitution rule. Now formally, the theorem looks like this. Again, we have an interval, so let I subset of R. We want an open interval. We want a function g on that open interval that is continuously differentiable. And we want a function f. F is defined on the image of g, so g of I, and also maps to R. And that function is continuous, so that we can integrate. Then I'll give you the version with limits first. For a, b in I, we have the following relation. The integral of f of g of x times g prime of x dx from a to b is the same as the integral over f of y dy. So that is this capital F. And we need to evaluate that. We scroll up here. We need to compute capital F, and we need to evaluate that at g of the bounds. So instead of the O bounds, we now get g of A and g of B, right? And that is why I wanted to have the bounds in here. So this is that version, or as an alternative, we can also formulate this in terms of indefinite integrals. So f integral of f of g of x times g prime of x dx is then the integral of f of y dy, where y is g of x. Now that may not sound very nice and handy, but on the other hand, it's not that complicated to actually compute an integral using this rule of substitution once you get your substitution right. And that's the decisive part here. You need an integral of that form to be able to use that rule. So the complicated part is to find a function g such that the integral has that form f of g times g prime, and then be able to integrate over f. So the outer function that you get must be one that you can easily integrate. And that complicates things quite a bit. So the crucial part here is to find the right substitution, the right g for that idea. Now, so that you don't have to remember that formula, there is a formal procedure that makes that a little easier to remember. And I'll first present you with that formal procedure in a very formal way. Don't be intimidated by that. We'll see an example right after that that demonstrates how to actually use that. Yeah, but unfortunately, to make this technically halfway correct is not easy to write down. So let's have a look at that remark here. So what we can do is this formal procedure, the following formal procedure is useful to apply this rule of substitution correctly. And just to be clear, this is by no means something that I would consider mathematically sound, at least not with the tools that we have presented so far. There are ways to actually make this precise, but they are pretty deep, and we are not going to discuss these tools in the context of this course, unfortunately. So let's say we want to determine an integral. So we have an integral over some function h of x dx. And we want to use a substitution. And that substitution is going to be y is g of x for some function g that we just guessed. Then the first thing that we do is we determine g prime, basically. So we determine dy over dx, and that is g prime of x. We take this y of x expression and differentiate that with respect to x. And then here comes the very imprecise act. We now take this here as an equation and treat these as formal entities and just solve for dx. So solve this equation for dx. And if we do that, we get dx equals dy over g prime. Next, of course, we also need to determine the right function f. So we're going to have to solve once again. We're going to have to solve our substitution, basically. So we have this y equals g of x, and we're going to solve that for x. So basically x is the inverse of g of y, right? And then that means what we get is the integral of h of x dx is the same as the integral of, well, we just solved x equals g to the minus 1 of y. So this now depends on y, times And instead of dx, we now use dy over g prime of x. And of course, again, there's now an x appearing here. Here is g prime of x. Again, we have to substitute that by g to the minus 1 of y. So formally, this integral now becomes quite complex. Copy the first part. Yeah, then there's the second part, 1 over g prime of g to the minus 1 of y dy. And now we have an integral that depends just on y. We can integrate that, and we can revert the substitution afterwards, if necessary. And now, of course, all this stuff here, this solving and these complex computations, that's usually not necessary if you do it right. Because if you do it right, you will more or less get this expression here automatically. If you don't, then probably the substitution that you used is not a very good guess. But as I said, let's have a look at a few examples, and I'll demonstrate how it's done. So, first example. Let's compute the following integral. We want to compute the integral of x times sine x squared dx. Now the substitution that we're going to use the problem here is obviously the x squared inside of the sine. We cannot compute the integral of the sine of x squared. So what we're going to do is we're going to substitute y for x squared. We will be able to compute the integral of a sine of y. No problem at all. So let's see if that works. Now, if we do this, as I said in our procedure, we first compute dy by dx. So we differentiate this expression with respect to x. And that yields 2x. So and now we solve this equation here. We get dx equals dy over 2x. And now let's take that back to our original integral. Remember, we have this integral x times sine of x squared dx. First, of course, we use our substitution here. So that is x times, we'll just copy the x for a moment, and then we have sine of y instead of x squared. So this is this solve for x thing that we did in the formal review here. And then we add times dy over 2x. Yeah, so we replace dx by this expression. And now the magic happens. And that's the crucial point here. Some magic has to happen at some point with this rule. We have x here, we have x here, and that cancels out. And that means we do not have to care about solving for x stuff anymore. So the x, somehow we must get the x out of that integral to be able to integrate for y, right? So now we get is 1 over 2 sine of y dy. And of course, that is now something that we can compute. So we take out the 1 over 2. Integrating the sine amounts to the negative cosine. So we have minus cosine of y, plus, of course, a constant. And now we revert the substitution once again, and we get minus 1 over 2 cosine of, and remember y is x squared. So we get this x squared here. And finally, that yields the correct antiderivative, the correct indefinite integral. So this is how you apply the rule of substitution. One more example, just to be sure that you got it right. Pretty similar example, actually. let's compute the integral of x times e to the minus x squared dx. Again, we want to do substitution. And again, the x squared is obviously what's troubling us. So in this case, we can even take it so far to substitute minus x squared for y. And then we get dy by dx is equal to minus 2x. So dx will be equal to dy over minus 2x. And then let's take this integral here. Do the substitution. So then we get x times e to the y times 1 over minus 2x dy. And again, what happens is the x cancels out. So we just get rid of that unwanted variable. And we have minus 1 over 2 e to the y dy. And of course, that's easily integrated. That's just minus 1 over 2 e to the y plus some constant. And again, we revert the substitution here. Minus 1 over 2 e to the minus x squared plus c. And of course, as I said in the formulation of the original theorem, instead of reverting the substitution here, if you have an integral with bounds, then you can instead just apply the substitution to the bounds. So in that case, remember, work like this. So you have this integral here, the last one that we had in our chain of integrals. And you just change the bounds from a to g of a and from b to g of b. So you apply that substitution rule to the bounds as well, and then you can just use these instead of reverting the substitution. Yeah, so that's useful for integrals with bounds, with actual bounds. Some examples of this will of course be on the exercise sheet as always. And that concludes our introduction into integration rules. So those are the most important integration rules that we have to collect. One more thing about integrals that I'd like to discuss with you is integrals with bounds that stretch to points that are, let's say, dangerous in one way or the other. And the most important example for that would be a bound that is infinity or minus infinity. So what we want to do there is we want to combine the idea of limits with the idea of integrals, basically. And that's going to be the topic of one of the upcoming videos. And as usual, I'll see you then.